Good morning, Math 30s. We're moving on to a new chapter, which is going to be called Radical and Rational Functions. And this video will correspond to my note package, and the note package will be lesson 1 that we will go through in this video. At the end of this lesson, I'm going to do 2 challenging homework questions. So please make sure that you are watching for that as well. All right, so let's quickly talk about what a radical function is. So radicals you were first introduced to in Math 10C, and a radical function is essentially the square root sign. So what's going to happen is in order to have a radical function, we're going to be given an original function, y is equal to f of x. And in order to make that a radical function, you're going to take whatever the function is and you put it underneath a radical sign, and then you there have a radical function. So what we're going to do now for this question here is we're going to take y is equal to x, and you know that y is equal to x, that's a line, a linear line that's going to go through, and I'll just quickly show you. So y is equal to x. Here's the equation of y is equal to x. And what we're going to do is we're going to take this linear line here and we're going to transform it into y is equal to the square root of x. So the first thing that we need to do is we need to get some coordinates. So I've given you some x values here. So x is 0, 1, 4, 9, 16, 25. In order to figure out what the corresponding y values are, what we're going to do is we're going to take the square root of 0, right? So in order to get, if y is equal to the square root of x, you put whatever the x coordinate is you're trying to find, and it will give you the corresponding y coordinate. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. And square root of 25 is 5. If you were to plot these, these would be your coordinates. So let's plot 0, 0, 1, 1, 4, 2, 9, 3, 16, 4, and 25, 5. This would be a graph of y is equal to the square root of x. So y is equal to the square root of x. So it's taking that graph here, which was the linear graph, and transforming it into y is equal to the square root of x, and this is what our graph looks like. I often tell students you need to be able to visualize certain graphs. So for example, if I say to them, okay, y is equal to x squared, what you should visualize in your mind is you should be able to see a parabola opening up. I want you to write down somewhere at the top of your page, y is equal to the square root of x. What you need to visualize in your mind is the shape of it starts at 0, 0, and then that is the shape of a radical graph. Okay, so if I go to my calculator and I now type in the square root of x and I hit graph, this is our classic radical shape. Let's answer a few questions about this graph. So the intercepts of this graph, the intercept is right here, and that point is at 0, 0. So both the x-intercept and the y-intercept are 0. The domain of this graph, I'm going to give it to you both in set builder notation and in interval notation. So the domain of this graph, the smallest x value is 0, and the biggest x value, it goes to infinity. So if I was to do that, express that in interval notation, it would be 0, infinity, and remember infinity always gets a rounded bracket. If I was to do this in set builder notation, I would have x is such that, and then I would say x is greater than or equal to 0, comma, x belongs to the set of real numbers. So this x belongs to the set of real numbers, it just means that I could have a value that's a decimal, right? I could have 10, I could have 11, or I could have any number in between, and that will be on my graph. So that's the domain of this graph. The range of this graph, the smallest y value, I hope you see, is 0. And the biggest y value, the graph extends forever upwards, it would be infinity. So the range of this graph in interval notation is 0 to infinity. And in set builder notation, it would be y is such that y is greater than or equal to 0, comma, y belongs to the set of real numbers. Okay, now what we're going to do on the next example is we are going to start transforming our graph. So remember I said we would bring in transformations. So transformations we're going to see in every single chapter. So if I take a radical graph, y is equal to the square root of x, I could transform it and I have the exact same parameters as we did with transformations. So here's my a value. And remember that your a value is your vertical stretch. And my h value here is my vertical translation. Sorry, my h value is my horizontal translation. My k value is my vertical translation, so that's going to move my radical up or down. And my b value, that's my other stretch, that's my horizontal stretch. Okay, looking at this transform graph here, so what we had was we had y is equal to the square root of x, that was our original function, and then that underwent several transformations to give us 3, and then negative x minus 1, right? So the original graph, and here's our transform graph. Now, just like in transformations, make note, you always want to make sure that the b value is factored out. So b value factored out. And this b value is in fact factored out. I'll show you after we finish this question a b value that wouldn't be factored out, but we're lucky because this b value is. All right, let's write our parameters down, and then we'll talk about the meaning of each parameter. So that's my a value, and that's 3. This is my b value, and it's negative 1. And this is my h value. So the h value is 1. Okay, talking about the meaning of each parameter. So the a value of 3 is a vertical stretch, right? So a is 3 is a vertical stretch. So we're going to say that is a vertical stretch by a factor of, and 3 is our answer. So vertical stretch by a factor of 3. Now our b value is negative 1. So you wouldn't say horizontal stretch by a factor of 1, right? That doesn't really make sense. What you are hopefully seeing is that if your b value is negative 1, yes, b value is horizontal stretch, but it also has to do with a horizontal reflection. So that negative 1 is going to be a reflection. So the second, discussing the second parameter, what's happening is we're having a horizontal reflection, and you have to tell me which axes. So remember that with horizontal, x goes to negative x. So a point here is going to be bounced over here. So x goes to negative x. And what that means is we're cutting the y-axis. So it's a horizontal reflection in or about the y-axis. Okay, the third transformation that's happening is a translation. So this h value is going 1 unit right. So we have a horizontal translation 1 unit right. So those are the transformations that are occurring. And what we're going to do to figure out the coordinates of the new point is we're going to map. So from the transformations unit, we know that x comma y, the new coordinate is going to be x over b plus h, a times y plus k. So an original point on my graph is going to be x over b. Now b is negative 1. So instead of writing x divided by negative 1, you could if you're comfortable with that, but x divided by negative 1, that's really negative x, right? I hope you see that. So if like x was 2, 2 divided by negative 1 is negative 2. And then I'm going to put my plus h in, and my h is 1, so I'm going to put plus 1. From there, it's a times y. My a value is 3. So 3y, and there was no k value. The graph is not going to move up or down. Okay, From there, they give us 3 really nice points on the radical graph, and we're going to transform those 3 points. So I've got 0, 0, and I've got, that would be 4, comma 2 is my second point. And my third point, what was my third point? This guy here is 9, comma 3. What I would recommend doing is I would recommend pausing the video, calculate what each new transform point would be, and then you could unpause the video to see if you did that math correctly. So if you did it correctly, your new points of your graph are going to be 0, 0 is going to move to 1, comma 0. 4, 2 is now going to be negative 3, comma 6. And 9, 3 is going to be negative 8, comma 9. So let's get those points plotted. So 1, comma 0 will be here. And then we have got negative 3, comma 6. So that is going to be here. And then I'm going to have negative 8, comma 9. So negative 8, comma 9 is going to be here. Now, before you connect those 3 dots in a nice curve, because we are cutting the y-axis, I should find out what that y-intercept is. So in order to calculate a y-intercept, what we do is we let x equal to 0, okay? So we need to take the equation of our graph. So the equation of our transform graph was y is equal to 3 negative x minus 1, close that bracket. And what I need to do to find out my y-intercept is this x is going to be 0. So rewriting this, y is equal to 3, negative 0 minus 1 is negative 1. Y is equal to 3 times the square root of, this is really a negative 1. Negative 1 times negative 1 is positive 1. From here, y is equal to 3, the square root of 1 is 1. So the y-intercept of my graph is 3. When x is 0, y is 3. I need to put that point on. So going back here, when x is 0, y is 3. So now what I could do is I could connect my dots with this like nice curved line. And I'm going to continue the line. I'm a little bit off that dot, so make sure yours is going through the dot. And this would be the graph of my transformed function. Before we go to the next slide, I just want to show you what I was talking about with taking out the b value. So let's just say you had this. Y is equal to, say we had 2, and then we had 3x minus 9, and then let's say we had plus 4. Okay, so this a value is 2. The k value is 4, so it's going to go up 4. The b value and the h value, I can't clearly see. Yes, the b value is going to be 3, but the h value is not positive 9. So you need to factor out that 3 to get 2. Take out the 3, and you would get 3, sorry, not 3. 2, factor out the 3, and you would get x minus 3 plus 4. So once you factor out that b value, I hope you could see that your b value would be 3. So your stretch factor would be a third, 1/3. And your horizontal translation would be 3 units to the right, not 9 units to the right. Okay, going to this slide here. So just very quickly, what they're asking is you take your original graph, and we're going to transform it to y is equal to a, get all your parameters in there. So b x minus h, close that bracket. And then your k goes on the outside of the radical, so plus k. Alternatively, remember you could write that k with the y, so you could say y minus k is equal to this function here. So a couple of things. It says identify the domain and range of y is equal to the square root of x. So here's my original radical, And remember I said you just have to be able to picture that in your mind. That radical looks like this. So if I said, okay, well, what's the domain of that radical? X is greater than or equal to 0. What's the range of that radical? Y is greater than or equal to 0. What are the parameters that affect domain? So the parameters that affect domain are what are the parameters between A, B, H, and K that affect the X values? And remember in my transformation, it's X over B plus H. So the parameters that affect the domain are going to be the B value and the H value. Alternatively, the parameters that affect Y, we know that in our transformation, it's A times Y plus K. So the parameters that affect Y are my A value and my K value. Okay, let's do this function here. So what we're given is we are given this function is our original function. F of x is equal to 3 minus 2x. So that is going to be a linear function. And what we're going to do with that linear function is we are going to transform it, and we want to put that function underneath a radical sign. So y is equal to, you take this function here, and it wants you to put it underneath a radical sign. So 3 minus 2x. So what we're given is our original function is in the form of y is equal to mx plus b. This is the graph of my original function, okay? What we are going to do is we are going to graph now from this original function, well, what would the radical function look like without punching in on the calculator? So a few things I want to talk about before we start figuring out points. In order to figure out the domain of our radical function, we are going to look at something in the radical graph here. And what we're going to look at is we are going to be looking at this radicand. So in order to figure out the domain of your radical function, you always take that radicand, so it's 3 minus 2x, and you're always going to say that radicand has to be greater than or equal to 0. So why did I say it has to be greater than or equal to 0? The reason is you know that you could never take the square root of a negative number, right? That's impossible. So whatever I put underneath my radical sign, it must be 0 or bigger than 0. So in order to find the domain of my radical function, you take the radicand and you make it greater than or equal to 0. You're then going to solve this inequality for x. Now, I always want students to keep their x value on the left-hand side of the inequality. So get rid of that 3. So we would have minus 2x is greater than or equal to negative 3. Then you're going to divide both sides by negative 2. And I hope you remember from inequalities, when you divide both sides of an inequality by a negative number, what happens is this inequality sign flips. So the domain of my radical function is going to be x is less than or equal to 3 over 2 is the same thing as 1.5. So you'll see that when we get to the domain, without even graphing this, the domain of my radical function is going to be x is less than or equal to 1.5. That's going to be the domain. Okay, how do we figure out what our points are on our radical function? So we need points on our original function. So over here, I've given you the point, if x is negative 2, so here's negative 2, the y value, the corresponding y value is 7, right? So when x is negative 2, if you plugged it into this function here, the corresponding y value is 7. If x is negative 1, the corresponding y value is 5. If x is 0, the corresponding y value was 3. When x is 1, the corresponding y value is going to be 1. And when x is 1.5, right here, the corresponding y value is 0. So these were coordinates, so negative 2, 7, negative 1, 5. They were coordinates on my original graph. Now what we do is to get coordinates on my radical graph. So the original, so I'm going to take this coordinate, so -2, 7. On the radical graph, what we do is we take the square root of the y value. So on the radical graph, it's going to be -2 and the square root of 7. And the square root of 7 is approximately 2.7. So my new coordinate on my radical graph is going to be -2 and 2.7. If I was to do this coordinate, so -1 and 5, -1 and 5, that coordinate on my radical graph would be -1, and on the radical graph, we take the square root of 5. And the square root of 5 is going to be approximately 2.2. So this next coordinate is going to be -1 and 2.2. The third coordinate, my x value is going to be 0, and my y value is going to be the square root of 3. And the square root of 3 is 1.7. This coordinate, my x coordinate, is going to be 1, and my y value on the radical graph is going to be the square root of 1, which is 1. We're going to star this because this point didn't change. It's going to be called an invariant point. My last coordinate is going to be the same x value, 1.5, and the square root of 0 is 0. This as well is going to be an invariant point, which we'll talk about after. Remember that invariant points are points on your original graph that don't change. They're also on your transform graph. Okay, so let's graph these points. -2 and 2.7 will be approximately here. -1 and 2.2 would be about here. 0 and 1.7 would be about there. That's my y-intercept. 1 and 1 would be there. That's invariant. It's the same point on my original graph of my transform graph. And 1.5 and 0, again, invariant point. Okay, what's sort of the most important? Students can see how these are going to connect. You have to figure out how you're going to connect these 2 points. If it's a radical graph, it's a curved graph. So you're going to draw a curve above that line, connecting those 2 points. And then you could simply extend your line. That's going to be the graph of your radical function. Okay, so let's do a couple of things. The domain of my graph, as you could see, is x is less than or equal to 1.5 of my radical graph, and that's correct. That's the biggest x value on that purple graph is 1.5. The range of this radical graph doesn't change. Y is greater than or equal to 0. Or sorry, it does change from the original. The original range was y is a set of real numbers, but this graph is y is greater than or equal to 0. The invariant points of my graph, I'm going to get you to write something about invariant points. So on radical graphs, invariant points occur when y is equal to 0 and y is equal to 1. So on all radical graphs, invariant points are going to occur when y is equal to 0 and y is equal to 1. So if I go to my graph, here's y is 0. That's going to be an invariant point. And that coordinate was 1.5 and 0. Here's y is equal to 1. That's going to be an invariant point. And that coordinate was 1 and 0. So invariant points, sorry, not 1 and 0, that point would be x is 1 and y is 1. Invariant points on radical graphs always occur when y is 1 and y is 0. Okay. This next graph, we're actually going to come back to this after we do the next question. I'll come back to this. So let's do this graph here. So what we're given is we're given a linear graph and we're going to make a radical graph from it. First thing I want to do is I want to talk about what the domain of my radical graph is going to be. So when we're doing the domain of our radical graph, what I want you to do if you're given a picture is you look at the original graph. So when we're finding the domain of our radical graph, you always look at the original graph. And what you're going to look for is where is the graph, so where is f of x, or in this case it's g of x, where is that graph greater than or equal to 0? So what I'm talking about, this is my graph here, and 0 is right here, right? This is y is equal to 0 there. And what I want is, what is the piece of the graph where my graph is greater than 0? And it would be this piece here. Okay, so on my original graph, you're always going to look at the original and you're always going to say, where was that graph greater than or equal to 0? Where were the y values bigger than 0? And this pink piece is where the y values are bigger than 0. And some students will say, well, why can't I have like y values less than 0? Well, you know from the previous example, we always square root the y values. You can't square root negative y values, so we don't include this piece of the graph. So if I was only to look at this red piece here, and I said, well, what's the domain of this piece? You would say, okay, the smallest x value is that guy there, which is -1. So the domain of that is x is greater than or equal to -1. So this pink piece is greater than or equal to -1. This is going to be the domain, and you'll see it when we graph it, and I'll graph it in green. This is going to be the domain of my transformed graph. All right, let's figure out what the transformed graph is. So the first step is you always want to mark the invariant points. And the invariant points we know are when y is 0 and -1. So go to your original graph and mark points where y is 0 and where y is 1. I might have said -1, I meant 1. So those 2 points are going to be invariant points. My radical graph is going to go through those 2 points. Then I need some other points on my graph of the original function. So let's take, for example, this point here on my original function. Let's take, I won't do it in blue, or sorry, in red. Let's take 1, 2. So 1, 2. So that point there on my transformed graph, which is the radical, it's going to be 1 and the square root of 2, because we always take the square root of the y values. And the square root of 2 is going to be 1, 1.4. Then let's take this point here. So let's take 2, 3. So x is 2 and y is 3. So let's take that point. And where will that be on the radical graph? It would be at 2 and the square root of 3. And the square root of 3 is 1.7. Okay. The last point on my original graph, let's take this point. So it's 3, 4. X is 3, y is 4. So let's take that coordinate. And on the radical graph, it would be 3 and the square root of 4. And we know that the square root of 4 is 2. So my new point is going to be at 3, 2. So let's plot these 3 new coordinates. And I'm going to do that in red. So 1 and 1.4 would be about there. 2 and 1.7 would be about there. And 3, 2 would be here. Okay, hopefully you could see the shape of your radical graph, and you just have to say, what do I do between these 2 invariant points? Because we're not going to connect them. We're going to draw a little tiny curve above it. So draw yourself a little curve above it, and draw your arrowhead, and that's going to be the graph of your radical function. And then if I said, well, what's the domain of this radical function? Let's see if we were right. We said that the domain was going to be x is greater than or equal to 1. And sure enough, the domain of this red graph is x is greater than or equal to 1. Going back to this slide here, if you have your highlighter, I want you to highlight where f of x, so where our original graph is less than 0. So this red line is our original graph, and here's where it's less than 0. These points on your radical graph, they are undefined. They don't exist. Why do those points not exist? Remember that this point here, for example, would be 2, -1. And if I said, well, where's that on the radical graph? You'd say, well, that doesn't exist, right? How could that point exist? Because we know that on the radical graph, we have to take the square root of -1, and that's impossible. So these points here on my original graph, they do not exist on the radical graph. Now let's look at, so if you have a different color highlighter, let's look at our graph where our original graph is greater than 1. So where the original graph is greater than y is equal to 1, so remember that this is our y value. So it's pretty much from here up. So this is my original graph. And they want to know, well, what happens to the points when y is greater than 1 on your transformed graph? Hopefully you see that that is going to correspond to these points. So on my transformed graph, on my radical graph, they are going to be below, right? So this was the graph of my original, and when I transform those and I take the square root of the y values, the radical graph is going to be below. Then the last piece to highlight that I want to discuss is going to be in between 1 and 0. So in between those two invariant points. So that's an invariant point and that's an invariant point. And what happens there is that our radical graph is going to be that little curve above, right? So remember I said we have to curve that guy? So in between, so my original graph, between 1 and 0, my radical graph is a curve above. And then this is asking, well, what happens when y is 0 and when y is 1? So hopefully we know by now when y is equal to 0 and y is equal to 1, those are our invariant points. And they're going to be the same on both the original graph and the radical graph. Okay, we are continuing on. And now what we're going to do is we are going to graph quadratics. So we just graphed a linear, and from the linear we graphed its radical. Now we're going to take an original quadratic and graph the radical. Okay, in order to do this, let's figure out the domain first. So remember in the previous example, I said that when you're doing the domain of a radical, what we look at is look at the original graph. So look at f of x. Where is that graph greater than 0? So if I go to my original graph, where are all my y values bigger than 0? I hope you see that this is where my y values on the graph are bigger than 0. Because remember, we can't take the square root of a negative y value. What you need to now do to figure out the domain of your radical graph is you just have to tell me what the domain of this piece is. So you say to yourself, okay, this is -3, and this would be -7. So the domain of my radical graph is going to be x is less than or equal to -3, greater than or equal to -7. So again, how you get the domain of the radical is you look at the original. Where's the original greater than 0? Where's the y values greater than 0? And then you tell me the domain of that piece. Let's now figure out what the graph of the radical will look like. So step one is you always mark your invariant points where y is 0 and y is 1. So here's y is 0. I've got 1 point, 2 points. Here's y is 1. I've got 1 point, and I've got 2 points. So I've got 4 points on my original graph that are going to be invariant. So they're always going to occur when y is 0 and y is 1. Okay, now we need other points on our original graph. So let's take this point at -6, 3. Let's take this point at -5, what would that be? 4. And let's take this point at -4, 3. The new transformed point, the x values stay the same, and you take the square root of the y values. So the x value stays the same, square root. X value stays the same, and square root that y value. The new transformed point is going to be, and I'm going to do this in red, it's going to be -6 and 1.7. It's going to be -5 and 2, and it's going to be -4 and 1.7. Let's graph that. So -6 and 1.7 would be here. -5 and 2 would be there. And -4 and 1.7 would be here. So I'm hoping you could see the shape of this graph. And then if I said, okay, well, from here, how would you connect? So the only thing you have to think about is those invariant points. And remember, you always draw, so in this one, it would be the curve above it. And here as well, you got to draw that little curve above. That would be the graph of my radical function. Let's check if I did my domain correctly. So I said that the domain of my radical is going to be between less than -3, which is these points here, and it's going to be greater than -7, which is those points there. So I did that correctly in order to get the domain of my radical. Let's do one last question. And we're going to be doing a same parabola, except it's going to be have a positive a value. So let's look at this. Now, I always like starting with the domain of my radical graph. So I get that from looking at my original graph, and I need to look at the piece or pieces of the graph where it's greater than 0. That's a little bit off. So this piece of my graph is greater than 0, and this piece of my graph is greater than 0. When you have two different pieces, that's completely okay. You just have to tell me what the domain of this piece is and what the domain of this piece is. So this pink piece on the right, I hope you guys realize that that would be 5, and this piece of the graph would be greater than 5. So my first domain is going to be x is greater than or equal to 5. And then because I have a second piece, I could say or. Now I have to talk about the domain of this piece, and the domain of this piece is x is less than or equal to 1. And you're going to see when we do the radical graph that the domain will in fact have two pieces to it, or the radical graph will have two pieces to it. Okay, step 1, mark your invariant points. Invariant points are when y is 0, so those are going to be on the graph of my radical, and when y is 1. Those are going to be on the graph of my radical. From here, I need a couple of other points. So I'm going to take this point here, which is 0, 5, and 0, 5 on my radical is going to be at 0, the square root of 5, which will be 0, 2.2. And then I'm going to take this point here, which is 6, 5. So x is 6, y is 5. So 6, 5. The new point is going to be at 6 and the square root at 5. and that will be at 6, comma 2.2. And I'll put those in red. So 6 and 2.2 would be this, and 0 and 2.2 would be this. So we have two different pieces. One piece of my radical graph is going to look like this. And on the left-hand side, it's going to look like this. Okay, so that is going to be the radical graph of this original function, which is f of x. So let's check our domain. So I said that the domain of my radical is going to be greater than or equal to 5, and that would be that piece there, or less than or equal to 1, and that would be that piece there. So that's correct. If I was to do the range of this radical function is just y is greater than or equal to 0. For your homework for this, there are two questions that are just very, very good, but they're difficult questions. So I'm going to make a video of those two questions. And what I'll do is I won't make it in this video. This video is long enough. So I will make a second part that will have those two questions done.